Yeah, good morning, everyone. Yeah, this is Jongwon Kim from Chit, Gwangju, Korea, and we also have Eric Yan. Yeah, who is co-chairing this cloud working group. Also, we have one co-chair, but he cannot join us today, but he will do the remote presentation. And anyway, so it's my kind of first physical after COVID. So it's really nice to see you guys face to face. And then we will start. Okay, our say cloud working group program, I just found that it's not listed online. We sent it out last weekend. Sorry for the delay. Anyway, the three kind of speeches from so Taiwan and Japan and Korea will be given. So mostly our chairs are doing the homework talks. So then we'll start from Eric. Yeah, he will talk about I can you mention your title? Sorry for that. I didn't have it here. Yeah. So anyway, he will probably introduce himself and we'll start talking. Oh yeah, Science Cloud for Sustainable Development. Please welcome Eric for his talk. Yeah. Yeah.
Thank you so much. Really nice to see you all here. I'm sharing the experiences we are doing in Taiwan, supporting the different scientific applications and also regional collaborations, especially related to the sustainable development. Let's start it from the self-introduction. Our center, Academic Integrated Computing Center, actually we are founded for the participating in the WCG collaboration, the worldwide grid systems supporting the largest high energy physics experiment coordinated by CERN in Geneva in Europe. Started from the early 2000. And from the beginning, we are serving as a Asia Center, supporting the participating sites in Asia, joining the collaborations. In parallel, we learn from the collaborations and making use of the core technology, the same core technology, supporting the scientific applications in different areas. Learning from the WCG collaborations and making use of the same infrastructure, supporting other scientific applications in different disciplines. From 2006, for example, the drug discovery, the earth science, and other compute intensive applications. After that, from about 2012, we started to move in to the distributed cloud. That means to making use of the distributed infrastructure to connect cloud resources together as the infrastructure. That's also what is been doing by the WCG in the recent decade. The last thing is that because we are also running a data center supporting thousands of CPU cores and also tens of petabyte disk storage. So the efficiency of the infrastructure running the data center or supporting the applications is also very, very essential for us. Later in my slides, I will introduce some of the status of our data center. For example, the power consumption. We use about 10,000 kilowatt hours every day for running our data center. The latest update of our center is from 2003, it becomes the course facility for big data analysis and also scientific computing in Taiwan, supporting the academic applications and also the collaboration with the industry. Based on the high energy physics core technology, as I mentioned, the same, the infrastructure is the same, keep evolving together with the WCG. It's a very important for us, and that's also what I like to share with you is to learn from the global collaborations, learn the advanced core technologies together with the scientific applications like WCG. So here's some of the blue box, the collaborations in different disciplines, as I mentioned, started from the high energy physics and extended to other computational sciences in different disciplines. And in the infrastructure and also the computing service parts, because it's a distributed infrastructure. So the authentication and authorization infrastructure is very important. That means every user around the world could access the resources, no matter who is providing the resource. The resource itself or the infrastructure is also distributed. That's the essence of the WCG, Worldwide Large Hadron Collider Computing Cloud. That's also the the cores of the distributed cloud. So you can have service provisioned by the center in Thailand or by the services hosted in Amazon around the world or in different any countries, and the user to access to those services shared through this infrastructure based on the authentication and authorization. In the beginning, the collaboration is making use of the X.509 certificate for the authentication for the user, authentication for the user, for the people, and also for the service and also for the hardwares. Now it's moving to token based. For example, you can use the OpenID using your Google account or your Facebook account, and then you could be authenticated. That's the popular OpenID. And then based on your user profile, you were authorized because of different roles in the whole systems. That's the we call it AAI, authentication authorization infrastructure. That's the first interface for the user or any services to get connected in the global infrastructures. So based on the user's requirement, we also support in the middleware and application environment. I will show you some of the examples. Access through the Jupyter Lab, through the web browser, or to access the machine learning framework or other services. So in the underlying, we provide the computing resource, the storage resource, CPU or GPU, and of course, supported and connected by the internet. So based on the monitoring and control to be more intelligent, supported by the machine learning technologies, we optimize the efficiency of the data center. The circle here is the because we are from the academic institute. Almost all the users are now from the academic institute. So based on the research workflow, we develop the services and also the required systems for the users. That's the basic ideas. So in general, the high level logical architecture of our system is like this. It's very simple. Currently, for the WCG, they have dedicated services and resources because they can make almost fully use of those resources, just like dedicated resource through the storage system, the EOS, and also the provided it by the RAID framework. For the other e-science applications, we are now based on the safe biosystem, which is a parallel very reliable file systems, and also supporting the block and also other storage services. In the lower level, that's based on the radio coding, supporting the reliability of the data management and also access. Upon that, that's the green box. Based on the requirements from the different applications, from computing, from cloud service to digital repository, research collaboration, etc. We're supporting the cloud storage service, the different research applications, and also the research data management, such as the Zenodo. From early this year, from last month, we started to set up the tape libraries as the backend storage for all the scientific applications. Some of you might heard of the case studies. We are working together with the disaster mitigation working group in Japan. We started with the support from Philippines and many partner country of Japan. We started from this case study. That's a super typhoon Haiyan, which caused thousands of life losses in Philippines. And based on the numerical analysis and also the improvement of the numerical models, we can reproduce the whole life cycle of this super typhoon from its born in the Pacific Ocean to the impact of the storm surge to the land. So traditionally, it's very difficult to simulate a super typhoon such as this one because of to the lowest pressure and also to the strongest wind velocity. In the traditional model, it's not possible to be such accurate. With the collaboration with the scientists from the atmosphere and also the oceanic areas. So they work together and improved the numerical simulation models, including some of the effects from the eyewall systems of the strong typhoon like this one. So it's now possible to be more accurate than the conventional simulations. So we can have better risk analysis for a typhoon like this one. So that's the basic ideas. So in the based on the supporting of the high performance computing and also working together with those scientists from the atmospheric or from the ocean or targeting on the hazard risks common in these regions, we are able to have better risk analysis for the natural hazards such as this one. So that's the basic ideas of the collaborations. And then the next step is that we share the knowledge and also the numerical simulation systems we achieved with all the partners. So the partners could make use of these technologies for future events, for the hazards happened in different places, to supporting the risk analysis. That's the whole idea. Apart from the typhoon, we also have experts in tsunami. So it's possible to simulate the tsunami wave propagations caused by earthquake right now. So once there's a big earthquake happened somewhere under the sea, then it's possible to get the simulation result to understand the highest tide and also the arrival time, for example, within 30 minutes or shorter time, so that you can earn some time as a early warning for the tsunami if it's happening 1,000 miles away from the land. So it's possible do the early work. In this case, let's say about the biomass burning, right as now in this season in the Southeast Asia countries because of the biomass burning. So the simulation could understand how the biomass burning impact to the other countries in East Asia or to other Southeast Asia. That's the also could be understand the impacts from the simulations here. We just have such a case study and also new case study presentations in the first sessions today in the disaster mitigation master class. The tsunami case here is a event happened in Palu in Indonesia in 2018, which is a very interesting case caused by earthquake first and then also landslides impacts together compound to the simulation such as this one. In the lower right, that's about the thunderstorm initiated by Bangladesh because it's a very which caused also hundreds of life losses in Bangladesh. But the problem is that we need to have proper observation data from the ground. For example, the Doppler radar data for this part. Otherwise, it's not possible to analyze, to understand the analysis. Also, leveraging the collaborations of the space agency in almost every Asia countries. The Sentinel Asia, they already built up the cloud services and also the collaborations. Once there is any disaster happened, then the the country could request the satellite image resource from these cloud services, and all the space agencies could upload and share the satellite data they have, so that we can work together with the impacted countries for the analysis. And there's another application case here is making use of the satellite data. They could analyze the oil spill in the around the Philippines in which year? Probably from 2023. So in the disaster mitigation working group, we also extended from those numerical simulation to the application of the Earth observation for different applications. In Taiwan, we are also supporting the deployment and monitoring and also analysis of the sensor network. So we can collect the motion of the Earth, detect the movement of the Earth's crust, and also generate a intensity map in 2 minutes or 3. And in the right-hand side, that's a new project detecting the movement using fiber. So that's a very new. And our center is serving as a data repository and also cloud service, and also providing the data analysis directory, making use of the data stored in our systems. So as I mentioned, currently the basic way to access the resources from our center, the first one is you can submit by the commit mode using the SLAM systems. The other way is using the cloud services, just with the web browsers. So we also provide the customized services, as I mentioned in the beginning, based on the workflow of the data analysis. So we also federate the data from the experiment site, from the cryo-EM microscope sites, and also the analysis facilities. We combine these two services together and build up the analysis workflow for the protein structural biology user community, making use of the Cloud EM. And also we integrate the AlphaFold systems based on the user's needs. So in summary, we are providing the big data analysis services through the web browser, Jupyter Lab interfaces, and also the, for example, the machine learning framework based on the user's needs. So we've been developed a lot of web applications for the users. Just with web browser, you can finish your data analysis using our resources, either a CPU or GPU. From last year, we also deployed a research data management developed by other institutes in our academy. They called it Depositar, supporting, for example, the spatial temporal search, also the Binder hub through the Jupyter. That means it's possible to reproduce the shared applications once the code is open directly from this environment. And also it's possible to to federate the data source from Zenodo or other GitHub or CCAN, several popular used data repository over the internet. So it's easier to access those open data and also to reproduce the applications shared by the scientist group. Here's the demo. So the logic is the same, working together with the user community, with the scientist group, build up the case as a reference so that we can collaborate with broader scientific groups around the world. So the system we built is called DICOS, Distributed Cloud Operating Systems. So we make use of the Kubernetes as the containers for both the core services and also the user applications. And the safe systems, the basic structure like this one. So we have replications, we have the monitoring, we could also customize the storage systems for different user groups once it's special requirements is there. So from this year, we've been having about 9 petabytes managed by the safe systems. And from last year, we will have 4 petabytes increased every year to the systems. So from February this year, the system will grow to 13 petabytes, supporting those scientific applications. So regarding the energy saving of our infrastructure, the first thing, again, learned from the WCG collaborations. Now it's very important to understand the so per performance unit, how much power is required. So there's difference between the Intel and also AMD. Now they are targeting as the ARM because the ARM is more energy saving from the hardware. The other thing is that based on the experiences, quite large scale of the hardware deployment and also applications. In the last 5 years, almost 50% the power was saved because of the evolution of the hardware technology. So the renewal of the hardware is also quite essential in terms of the energy saving. The other things in our experiences is that if that's possible to manage, to optimize the power usage of the cooling system in our data center. Because apart from the the power consumed by the hardware, computing or storage, the cooling system also costs a lot. So we are before the analysis, we need to collect all the information from the cooling system as well. So we set up sensors in the air cooling systems. We collect the information in every 10 seconds. So based on those data, we the first thing is that we try to identify any anomaly of the cooling systems once it's happened. And then we can, for example, turning off the problem one and start up another one as a replacement. And that's one thing. Yeah. The other thing is that we found that the most efficiency measure is to just turn off the computing server once it's idle, once there is no many jobs waiting in the queue. And then when there is job coming, then you can turn on the hardware. So we can save about 20% of the powers used by the computing server. But the issue here is that how to make this decision intelligently and also automatic. That's what we are doing. Yes. So you need to have all the information of your computing server. You need to be aware of how many jobs are waiting in the queue. You need to know how to turn on and turn off the server, and you have to decide how many servers should be turned on or turned off in different situations. But that's a directions. So we have monitoring of our data center. And so in the past 10 years, that's the power. So the red line, that's the power usage of the hardware in our data center. The blue line here is the power usage of our cooling systems. So the decrease of the hardware is very significant, but the decreasing of the cooling is not so deep as the hardware. But the PUE is growing, unfortunately, but also because of the climate change. Yeah. I think I should stop here. That's some of the experiences in our center and also the collaboration with different user applications. If there's any questions, you are very welcome. Thank you so much. Yes.
So far, how many workers do you have for Kubernetes deployed? Resource, it's distributed, right? So everyone who want participate will also can join. So, so actually, how many servers are workers that under Kubernetes?
Under Kubernetes.
Yes.
Yeah. Yeah. In the future, all the resources could be federated, could be flexible arranged, so the users to see. I mentioned there are two ways to access to our resource, either from Slurm or either from. So in the next step, we will federate all the resources. Yeah. Either from Slurm, you can see all the tools. Now it's separated, but the next step will be federated. So in total, we now have 10,000 CPU cores, about 200 GPU boards of different generations, from A100, 3090, or V1.
Okay, when you're federating them together, you need some kind of, say, specialized scheduler, right?
Or
containerized. Yeah. So you already have developed something for
Yes.
that,
Yeah.
or developed.
Yeah. Or containerized.
Yeah, hi, question. Thank you so much for your talk. Very interesting work. So I actually have two questions. I guess the first one is about like you're saying turn off the machine. Are you referring to like completely shut down?
Yes.
Right? Can you,
Yes.
well, I suppose you could shut down in software, right? But to turn it on, you have to physically, no?
It's
Or like-
also possible.
It's possible.
Yes.
And do it through software?
Yeah. Yeah.
Okay.
In
And
less than 2 to 5 minutes currently to reboot
to reboot.
yes, a server.
and that would like save more power than putting into like
Yes.
sleep mode?
Yes.
Or like, okay, I see.
As we, according to from our experiment, yes.
Okay. Maybe
That's
I'll
the best
yeah.
efficient way. Yes.
Maybe I'll talk to you after this about
Yeah,
how
yeah.
to do that. It sounds
Yeah.
like a little bit of
If you make the
Interesting.
server in hibernation mode, still that will cost about 20 to 50% of the power as an idle machine. Yes.
right. Also, have you also looked into like the security on aspect of this? Like, for example, how do you provide like the isolation between each work node?
Isolation for what?
Well, you have the cloud, right? So there might be like multiple users running on the cloud. How do you like provide making sure that each user wouldn't touch other users' data?
The first step, of course, that's based on username and password. Now there are two approach. The next step is to be based. The other approach is to deploy the multiple factor authentication. That will make your system more secure. Of course, before that, only required service is provided. That's the rule of thumb.
All right, thank you so much.
Okay, thank you. And yeah,
your crowd to build your crowd. Can you describe a bit about those kinds of software? For example, do those software need to be customized to build the crowd?
Not necessary. It's quite easy to make use of the Kubernetes or
Just
the,
traditional-
OpenStack. Yes.
Okay.
Yes. Yeah. Just set up and also according to your environment. Yes.
So, would it be possible if we try to optimize this kind of software that can help to build a better, like create a better performance?
So you need to have users.
Mm.
You need to monitor your systems,
Mm.
how your user is making use of the resources, how to
Alright.
make the application more efficient.
Mhm. So based on the correct configuration, based on
That's right.
all right.
That's
Thank
right.
you.
The monitoring and control is very
Mhm.
important.
All right. Thank you.
okay. I think we now time for the next speaker. Yeah, let's thank the speaker
Thank you.
again.
Thank you so much.
And so we now have a second speaker from Japan, from remote. Let me introduce the title, Decentralized Resource Allocation for Beyond the 5G Era. Hiroki-san, are you ready? Is he ready? Yeah, he wants to be the yeah, it's done. Okay, he was in the meeting, Zoom meeting, but he's not present at this very moment. So I think I should go first and then wait for him joining. Okay, and let me see. Yes. Okay. He was in the meeting, so okay, it's shared. Okay, I think So my speech was supposed to be third one, but since he disappeared from the Zoom, Okay, he was there just kind of 5 minutes ago. Anyway, so let me talk about this. Yeah, my topic. Okay, the topic is live Express A services with digital twin cloud support. So this is kind of a partial refinement of the talks which I've been giving, and in this cloud working group, let me try to yet kind of say point again. So let me try to kind of update the basic concept which I've been talking. Yeah, but I've been talking about this so many times, but there are some of who is listening my talk first time. So let's see. The, the first thing X plus AI, right? Some of you may be curious, what are you meaning by that specific term, right? X plus AI. Usually I said, okay, X is kind of say domain, X domain data. Okay, X domain data will be linked to AI. So that can be translated into data and networking and AI, right? DNA. So why it's called the DNA? Data will be linked to the AI, right? Okay, so now you get it. And also one small thing, when I'm talking about AI, actually this is kind of say our, icon for AI. So it's Dream AI thing. So basically, okay, one more comment about it. AI in Korean word, there is some word called I. I actually means small children. So they will grow with some kind of the dreaming, right? So dream AI actually means, and the technology AI we are talking about, it's really growing fast, right? It's growing super fast. But anyway, some 5 years ago, when they are really start talking about AI, okay, they it was still quite young and small, but now it has grown so much. Okay, anyway, that is Dream AI. Anyway, DNA and Express AI is the same thing, right? Yeah, now you're getting it. And let me move on. So AI plus X, maybe you may want to think about how to use AI post domain X, but X should come first. It's more data, is more important, right? So that's why you're talking about it. Okay, so next slide. So also I'm talking about, everyone here knows about training and inferencing, right? I don't need to repeat about that. One thing which I want to add or highlight is the liveness of this thing. Okay, everyone, we have gone through, all those tests, right? Exams, right? You prepared, you studied, you trained yourself, and then you did the test, which is inference, right? But when your test result is not good enough, you have to study again, right? So that is kind of say this iteration is really important. But still, if you think of a real world AI problem, so this real kind of, liveness, whether you can refine your model kind of immediately when there is some problem or when some new kind of data is coming in, you have to do the refinement, right? So is it possible or not yet? So that is the kind of question you have to think about, because in the real world, so for example, so let me say real industrial world, like smart factories, this thing is becoming really important, right? So the liveness will be the key kind of measure of success for successful express AI deployment. So that's why I say liveness, live, this continuation of the refinement should be possible. Okay, so then another thing I usually talking about AI, yes, it's intelligence thing, but a lot of people say it cannot do the magic without you actually organize things in order, step by step ordering, which we usually talk about automation, one thing, another, everything is organized well enough, then data will be accumulated, that with those data, with the experience added, so the intelligence is coming out. So we are a lot of people talking about reinforced. Okay, a lot of it, yeah. The training method, it does not require less learning, less kind of experience, but still, it is needed, right? So basically, automation. So you have to do the think of automation first, then AI will come after it. Still, please remember this thing. So I'm talking about, so what kind of say basic environment, basic concept should be supported. And Eric just talked about this cloud thing, right? Kubernetes containerized. That seems very much trendy there. So if you're thinking of supporting this AI, okay, it's better to be cloud native one, right? That will be futuristic. That will save you from those locking problem. So you may have to pay too much for one special cloud vendor. So you want to be neutral, right? So cloud native is the very much possible solution for that, and everybody like that idea, so it's going there, right? Okay, another one, this data-oriented structure. Yes, data is really kind of say delicate thing. It's very hard to handle, and then so yes, allocating computing resource. Okay, it's allocating the table for people. Yes, it's pretty easy problem. Oh, of course, when there is more demand than supply, you are in trouble. But most of the time, it's just allocation. Yes, sit here, sit there, and then you can handle it. But about the data thing, it's very much delicate, right? So privacy or security and all those things, you have to handle it. And then some things are remaining by how you handle it. Go back to the say management of data thing, sharing of data thing is another one. So when you want dealing with that problem, so you have to think again from the start. Okay, usually I'm talking about this right hand side, you can see 3 layers. So in the bottom, you will see some word like points and rates. So I believe everyone here may know the term data rate, right? But smaller version of data rate, you may call them points. Points and the rates, should be connected. Okay, we were talking about connected sharing of data. That will be the baseline. It's more storage oriented level. So you have to enough storage space to be connected, which are usually called connected data rate. Then after that, a lot of people are talking about data pipelines. This term is also tricky, but it's really giving us challenges. So you have to can link some specific information, amount of data here and there, but let them really connect it. This time, we are not talking about connecting storage space. We are talking about the data itself should be connected together, which means actually analyzed together, integrated and analyzed together. That is a real challenge. It's pretty hard to make that happen because you have to bring all those data into one central place. Maybe the job may be easier, but the problem is usually you don't know which specific pieces of data you need to integrate them for your analytics, right? That is the problem. It's pros and cons of different approaches, distributed and centralized. A lot of problem there. Oh, it went up. So then on top of that, some people are talking about, you may heard of terms called the data fabric or data meshes. So this kind of term, which I personally like the term data fabric, or no, data meshes, because the information of specific information data you want to link together means some data here from one domain and another data from another domain, the weather data and then this kind of product, plant growth staging and all the different domain data should be linked together, right? The sense of they are linked together is matched together, like the matches, right? So then the term data matches seems like a very much ideal thing we want to achieve. But these matches should be supported by AI. AI inspired data matches is something we are talking. A lot of people are talking about it, but it's pretty hard thing to achieve. So it should be approached step by step, right? The bottom from storage and shared, and then process-wise pipelining, build up, and then eventually we may get the dream version of the data meshes. Okay, that's how I view this space. Okay, this one is kind of illustrative. A lot of talks for the I already mentioned this Dream AI log on top, but a lot of things are actually coming from, we are talking about cloud, we are talking about say servers, HPC servers, and the data storage servers. Okay, but how they are really kind of say managed? It's all those Linux operated. Usually all those servers, I believe you Agree, right? So those will be managed, right? But now they should manage it intelligently, or they should be managed for security, right? But these actually icons relate to some project called the eBPF, and then there are progresses there. So which want to secure your servers, okay? Then those servers close together, they will become part of the cloud. That's how all these open source based ones are linking. So I believe that's very much important. Also on the top, we have some concept called data warehouse and data lake, also lake houses. It's very much the technology trend, but all the way for this thing called from data lake to lake house thing is going up because we need faster and more huge data integrate together and analyze. Okay, so that's it. So let me see. So when I say Express AI services, it should be MSA, microservice architecture based, service chained or service composed at once. Okay, it should be based on containers, of course. And so now let's look at this thing. Okay, suppose those are kind of becoming the trend. What kind of things we should prepare? Okay, that's the thing. Usually I'm talking about this one. So yes, all the Linux boxes, but they should be controlled from this kind of say control tower. Okay, I don't have it here in the icon. Yeah. Then those control tower will manage monitor and control. It's just the term, yeah, monitor and control. Control tower should be able to see everything going on, visualize them, and then maybe people are now using terms called observability, right? So kind of try to understand what's going on with observability. Then you will try to allocate workload, different workload based on the user request. Then, but of course, securely, right? Okay, all the challenges are there, but the problem is now it should be happen everywhere. So what's important is this infrastructure. Yes, cloud is kind of shared infrastructure, right? And this same thing have to be spread over the world, over the globe. So then this is kind of so which I say open infrastructure should be there. And also the common platform. Okay, hopefully this cloud native, Kubernetes based one should be the law of putting them together. This kind of common platform should be based the same platform. It should not seek, it should be able to make this linking of resources to the services transparent. So that's the sense of kind of say common platform here. So that will help us to enable Express AI services. Okay. So let me continue this sense to link to how we can think of solving real world problem. And so let me talk three concepts. The first one. So now, yeah, now in this APN, there was more hypothesis, the HPC type of talks, right? So a lot of supercomputers are mentioned. So in that sense, high performance computing is one side. Okay. Then you do have something called the big data on the right-hand side. But here in high performance domain, you may want to call it high performance data analytics. HPDA actually stands for high performance version of big data. Okay. But then in the center, the same something called AI is there, right? So what I can say is okay, I'm checking the time. Yeah, okay, good. So HPC in one side, high-performance data analytics the other side. This very computing intensive, right? You know, CPU intensive ones, that would be MPIs and then HPC, and the other side, high-performance data analytics. It's more data dependent ones, a little bit of memory intensive computing. So you can think of that AI, as you know, they are becoming on the GPU and computing, GPU computing and data intensive, right? So you can think of this logic. But the good news is, okay, okay, with the cloud, we have Kubernetes-based ones. It's pretty easy to deploy. You can try to customize. Yeah, it's taking effort, but you can make it happen. It's pretty reliable. And so HPC, HPDA things are happening on top of this kind of data storage. So Eric mentioned about SAP. Also, we are also trying several instances of SAP. It's a learning over the years, and so we are becoming a little more confident about it. Still, I have to learn a lot from Eric to sustaining them. Anyway, so what I can say is they are based on open source. It does not cost you that much money, right? So cloud native computing is open source based and all this. So, but making them really learning and making them really into production and manage them is quite challenging, but it's doable. So that's what I can say here. So we also have experience of learning them. Okay. Also, the cloud native, yeah, kind of say computing. So cloud native. So NVIDIA also, they've been talking about this cloud native AI supercomputing. Yeah, but I added the HPC AI. It's because my view is HPC and AI they should go together at this very moment. So cloud native supercomputing is really the kind of direction. They also appeal for the real world production. It's becoming very much important and realistic. So what's for future? A lot of people are working on different problems, but disaster mitigation, it's also kind of seeing what's happening in our nature, right? If there are changes there, you want to monitor them, right? And then try to check whether this is kind of say what kind of situation, which is actually this twin thing, right? Now I'm going into the twin. So the cyber world, the thing and the twin part, digital twin part and the real world physical thing should be synchronized. Okay, here, let me just tell you, digital twin, there are kind of three M's. So the first M is mirroring, the second M is monitoring, the third M is MNS, modeling and simulation. These are three basic steps of a digital twin. So mirroring, so physical world should be mirrored into cyber world, digital world, okay? Then what's the second? Monitoring. So you should be able to update what's really going on, right, to the cyber world. So that's monitoring. The third step is MNS, modeling and simulation. You should be able to, based on those, let's say, cyber or digital model version, now you should be able to do the modeling and simulation. You will do the simulation based, analysis. So with that analysis result, you should be able to decide, right? So that's the MNS thing. After that, you may go into the federation or the higher level stuff, but three major M's, right? Mirroring, monitoring, and MNS. Okay, if you think of those, what should be your target? You may target small one